I would like to welcome you all to the first session on deep learning. So today, we're going to dive slowly into the concept of deep learning and how it emerged. So we will start first with the classical understanding or development of feature representation methods, how to represent features. So this is basically what sparked the whole field of deep learning. One of the main I would say like motivational problems in machine learning that led to deep learning. So in today's lecture, we will cover many things like how the pathway basically from ML to DL. And during this, we will see some fundamental principles. So we'll start with, I think all of you know what handcrafted features is. So since you've taken a machine learning course before this, and feature selection. So we will dive deeper into feature transformation and representation. We'll discover the concept of spanning sets and encoding and decoding in a very fundamental way. We will look at fixed, perfect spanning sets and fixed imperfect spanning sets, and also learnable spanning sets. So during this, lecture, we will also discover a very important principle, which is, which was actually pointed out by Da Vinci, centuries ago. So it's about simplicity. Simplicity is the ultimate sophistication. So basically, we will learn that the power of deep learning lies in transforming the data into new spaces, where things become much simpler to solve. And this is a very fundamental principle in deep learning. So transforming complex features into space where simple models can work. And so that's one thing. And what I think is the major breakthrough, the major discovery of this lecture at the very end is several typical super unsupervised machine learning problems can be formalized as what we call matrix factorization. So I know that we have seen PCA, k-means before, but in today's lecture, we will show that these could be formalized as mathematically as matrix factorization problems. And we will also show that deep learning can be written as actually a multi-layer matrix factorization problem, which is fantastic. So this is, these are the things that we're going to look at before we dive into deep learning, composition, backpropagation in the coming sessions. Okay, cool. So as you guys know, deep learning has dates back to not only, a few years ago. Actually, if you can see here, there are some original papers that were published where the concept emerged in the 1940s. So it's really old. And you may ask the question, well, what makes deep learning workable? These days, why it exploded and solved so many unsolved problems. So the story starts with backpropagation. So this trajectory is basically what we're going to explore during this deep learning journey together throughout these different sessions and lectures. So there are so many buried publications that they're hardly cited right now, but these have already sparked the concept of deep learning, including, for example, multi-layer feed-forward networks that was published in 1989. So this is when the paper was published, and it talks about, basically, it says it has been at the time. So this is something very interesting. It says it has been nearly 20 years since Minsky and Papert, conclusively demonstrated that the simple two-layer perceptron is incapable of usefully representing or approximating functions outside of very narrow and special class, right? But then this, basically a roadmap was blocked. People have shown that we can use them to approximate functions and learn representations from an input space to an output space, but this has changed throughout research. So you guys can see that later on that in the last several years, the researchers have begun to explore the ability of multi-layer feed-forward networks to approximate general mappings from one infinite dimensional space to another, from one input space to another. So we're going to look at all of these together, and it's like today we will talk about approximations, we'll talk about transformation functions, and these basically are the keywords that started the story of feed-forward networks and deep learning years ago. It's all about these functions that we want to approximate, okay? So at the end of the lecture, we'll have this, beautiful map to complete together, and it has a summary of the whole content of this today's session. So we will start with a quick reminder about supervised regression models, linear and nonlinear, also multi-regression models, and then we'll look at classification and the mathematical formulae. And then later on in the second part, which I think is the most exciting part, we're going to talk about spanning sets, matrix factorization, and representation learning. And we'll start with, we'll discuss 3 different cases. And then we're going to talk about making these spanning sets learnable. And we'll talk about PCA as a factorization problem, k-means, generalized factorization problem, and other examples, which we're going to discover together today, okay? So this map will complete it at the very end, and it will present a recap of the whole session. All right. Now, I think we can get started with the content. So let me just go back to this. All right, so let's start with this beautiful picture. So you guys, let's say have this photo, and this represents your data X, okay? So that's your input X. So this input X lives in a high dimensional space. Let's call it RD. So what are these D? What does D represent? D represents the features, the number of features. So the features here, the easiest way is, of course, to take one pixel and have the, like if it's black, you can take the average, for example, of the RGB channel, right? Or you can take 3 values there, right? So you can consider each channel individually. So let's say for the sake of simplicity, I turn this into a single value, like 0.8. So my vector will start with 0.8, and then, for example, the next pixel will be 0.7, etc., until I reach the very last pixel. So I just go through this image pixel by pixel, and then I'm going to get, for example, 0.5 here. So this is how I represent my sample X, okay? Now, the thing is, when you represent your sample X, then you would ask a question. You want to give this to an algorithm, right? So you want to give this, input this X to a model, and this model will answer the question, a question that you're asking. So for example, here, you can ask the model, is there a dog in the picture? And the model will answer, and this will be the output space. So this is the input space, right? So we have an input right here. So let me take a different color. Okay, so the input space, the output space, and the output will be a 0 if no, and 1 if yes. So here we have a yes. Now, the question that we're asking here, that first we extracted features, and this is what we talked about in the past machine learning link. So we had, we just simply extract features, but as you guys know, not all features are important, because if I ask you right now, and you look at this picture, what makes you say that this is a picture of a dog? All right. So you may think that if I just get the picture of the head, this part is, the most important part, that this is the relevant part, or these are the relevant features that I should be looking at or trying to find, right? So you kind of focused on the most important parts of the image. Maybe you can say, I don't need this whole box. I can only look at if I detect an ear like this, and if I detect an eye like this, okay? And I remove everything else. I can discover that this is a dog, okay? So what does that mean? This is what we call feature extraction, which means that, all of these features that I have in my d-dimensional space, right? Remember, guys, we have like multiple dimensions now. So each dimension represents a feature in of this image, right? So a pixel value, not all of them are important. So the key idea is that I don't want to extract all features. I want to learn how to represent, okay, this image or this sample X in a new space. And in this new space, I can easily discover that this is a dog. So basically this new space maybe will focus only on these regions naturally, right? So it will reduce all dimensions. It will remove all the other features. It will remove all these guys and remove and keep the ones that have these values, all the pixels inside these regions. So what happens to my space? My space goes from D dimensions to only maybe a few here, okay, a few pixels over here, and that would be D prime. So I will construct a new space where I have only, okay, D prime dimensions or like bases, and D prime will be smaller than D. So if I can solve this question, actually, it's very important because a lot of, as I mentioned, of the features are not interesting to get, and the goal is that to understand how to represent to extract the features. So for example, this is another example. So let's say you have this image. Okay, it's a bit blurry. We can work on different problems. We can work, for example, on regression problem. A regression problem will be to create a high resolution, okay, representation of the image. So you want to super resolve the image. So this is what we call super resolution, okay? So you go from an image that has been vectorized into this vector X, low resolution, right? And then you give it to my model, the super resolution model. And then I get the vectorized image that I can build back into the matrix. I can transform it back into the matrix, right? And then this would be XH, and this is a high definition image, okay? So now it depends on the questions you want to ask. So for example, here, when I asked the question, is there a dog? Is this a dog? Yes or no, is there a dog in the image? That's the answer I want to get. I want to get a 0 or a 1. But if I ask another question, I would not ask if there is a dog. I would ask, is there a dog playing here? So I change the question that I'm asking to the image, to the data. And is there a dog playing here? Now you think about the features that you want to extract. Which features you want to extract, guys, if you look at this? So if you think about it, we'll have first, is there a dog playing in the image? There are two things that you need to focus on. First, what characterizes a dog? And second, playing. So you have here an object or an item, and here you have an action, right? So it's action recognition and object recognition in computer vision. So it's a double task here. So action recognition, you're trying to find that this not a video, but you're trying here to at least recognize that it's playing. So this is very important. So this region is important, right? We agree, the ball, because it's playing. And then you have, for example, as I mentioned, the ear of the dog, and then maybe the eyes or the size of the nose, and you can, you can identify the dog. So these are very, very simple questions, but the whole field of machine learning and deep learning boils down to trying to understand how to represent this dog in an abstract space, a completely abstract space where we can, easily identify that, it's a dog playing with a ball, for example, okay? So now we started with this, and we're going to talk about how these are important questions. So first, I'll start with some preliminaries, and just to refresh your memory. So the first part of this lecture is simply preliminaries on regression, supervised regression, and classification problems, and how we formalize them using linear algebra. So first, let's start with a simple basic linear regression model. So here we have a linear regression model. So in a linear regression model, as all of you guys remember, we have an input X, right? And we have an output Y. So here the goal is that, for example, your input X could be, the picture of the dog, right? So this is a picture of the dog. And then the output Y could be the age of the dog. So given the picture of the dog, I want to predict the age of the dog. And this is, the input of your data as of your model is X, the picture, and then you give it to your model, and the model will give you your Y, which is the age. So this is a typical regression problem. And usually, as all of you guys know, so in regression problems, we do have an observation. So let's say this is my observation right here. So for this value, I'm going to read my my Y. So this is the ground truth. So here I do have my YP. So this is for sample P, okay? And this is the ground truth value. And if I try to predict a line that fits this data, so let's say we have actually multiple points, right? And then these are my data points. These are pictures of dogs, and they have different ages. And it happens that they fit what we call a linear model. So they fit this linear model. And here we can see that if we take one sample and then we project it onto this estimated model over here, right? So we're going to get the prediction, and this is my prediction. Okay. So the prediction right here is actually a projection, and this is my Y hat P. Okay, so this could be written in a very simplistic way. So the model is a projection onto basically a weight vector that represents the slope and the bias of this line. Okay, so it's like a linear model, and by projecting I get what I observe, which is the Y P hat. Okay, so it is written in a simple vector, basically transpose, and W is the weight of my model that I want to learn. And here you guys can see what we added, and we have seen this before, as I mentioned. So we have the bias. Because we add the bias here, we define what we call a compact form. And this compact form allows me to take into account any bias of the model. So we have the slope, and we have also the translation of the model due to some bias in the data that we try to account for. Okay, so you can see it's beautifully written as in linear algebra. And now what we have here, if we want to learn the W, right? So what we do is, as you guys remember, we need to optimize a loss function, right? So the loss function will enable me to start. So I start with a random W. So I had W0. My random guess is really bad. If I project these points, I'm going to have if I project, these points like this, I'm going to have very big errors, right? So which means that this model is not good. So I need to kind of find the model such that when I project the data, I have very small segments here, which means, it really approximate my data distribution and the relationship between the X and Y. So this is how we define the loss function. So from the goal is basically to have this model that we want to estimate, this W that we're after, right? So this is our parameter. Once we project the data onto this linear model that we have right here, parameterized by, so this is the linear model XTW, right? So once we do that, then we get our prediction, and hopefully the prediction will be close to the ground truth. So this is the ground truth. So we want to approximate the ground truth data, and the loss is a least squares cost that we have right here. So the least square cost, what is it, guys? It's basically the predicted YI for each sample I, okay? And then this is the ground truth. So this is what we have. This is the real score that we want to predict. And what we want to minimize is simply a distance between, a square distance between what we are predicting and the real ground truth value. So what we are predicting, as I mentioned, is a projection into this linear model. And here we simply sum over, all number of samples. So you may ask, do you guys remember why we call it least squares? Anyone here? So we call it least squares. Think about it. Look at this physically. So if we have, for example, for each point right here, right? So this is, these are the coordinates of the point, right? And then this is what I'm predicting for the point. So I am predicting this if I project it into my x, into my y. So I'm going to predict this, right? So this is yi hat, and this is yi. And this distance is actually, if I use a different color, this distance is my error. So my error here, when I square it, is actually I'm doing yi hat minus yi squared, right? Squared, it means you take a distance and you square it, so you're going to get a square, literally. So this is the area of this square. So we're going to sum up all these values. So my loss function that I want to optimize is actually a least square loss, because I want to have the least, the smallest cumulative or additional areas of these squares. So the smaller the squares, the happier we are, right? The bigger the squares, the bigger the error. So for example, this point has a very big square because it lies far away from the line. So that could be an outlier. So this one is not really good for our model, for our loss function, because it will be magnified. And when a data point is magnified, what happens? The loss function will focus on minimizing this primarily. So it will try to kind of make the model decrease the error, the loss. And the goal of decreasing the error is to minimize the area right here. So you're going to probably bias the model more towards this outlier that lies outside, of the main data distribution. And you can see that the main data distribution is around here. Okay, so this is, problematic. Not all losses are good. So we have seen different losses, and there is also the absolute value, for example, which doesn't magnify, because when you do the absolute value, you just calculate the distance between these. So it's actually yi hat minus yi, and then you sum over all training points. And this is the formula. And here you don't magnify the outlier, because what you have right here is just this segment. Okay, so it's less magnified than the least squares. So anyways, there are lots of variations there, but now we know that we can use the least squares, and the easiest way is to use gradient descent. So this is a convex function. It may not look like this, guys, but this is also a reminder, just, of how once we have the loss function, we need to get what we call the W star. So the W star is the optimal model that minimizes this loss. So the W star here, if you look, when I start to move this and try to find the best W, the W star would be somewhere around here, maybe. Okay, so that's my optimal model, and the optimal model is computable through the optimization process using gradient descent or stochastic gradient descent, any kind of optimization algorithms. And the goal is that if I have the loss function right here, so this is the function right here is L of W, and we have W over here, and you guys can see that this is how my loss looks like, and the optimal value is over here. So we can easily find this optimal value by following the negative of the gradient of the loss function. And by following the negative of the gradient, we can kind of roll a ball downhill until we get to the optimum. And here, because it's convex, it's actually a very good optimum right here. Okay, cool. So now that's regression, how we formalize it. So everything boils down to trying to solve this. And you will see this everywhere, guys. In classification, you'll see it also in unsupervised learning. So all these formulae are very, very similar. So now let's look at this together. So let's say we have a whole matrix. So this is, how we map this in a matricial form. And I strongly recommend that all of you write your math using these kind of visual displays, because they give you an intuition about what's going on in the data. So basically here, what we have for every single, if we take, let's take a single, like row. So this is a sample. All right, so I have my sample right here. Let me use a different color. So we're going to take a sample, and this sample, for example, sample I, all right, so this is sample I, xi. We will multiply it by the learned model, so this is W. And when I multiply it, I'm going to get, you know, like basically we'll predict the value yi, the score yi for this. So if this is, for example, one particular dog, so this is one particular image, all right, xi, then I will predict the yi hat, which is the age of this dog. And if I do the same, so I go and I do the multiplication one by one until I get to the last one. So this is the xn, the last image in the data. I multiply again by my mapping function, right, that I learned, and I'm going to get the yi hat. And hopefully our goal is to minimize the distance between the y, so here this is the yn, okay, the last one. So the goal is to minimize the distance between these two, and you can use multiple losses, and this is how you define your losses. What am I losing if I have, for example, the age 15 predicted and minus, for example, 10? So my error is actually 5 years. That's quite large, right? So that's the idea. So now, if you look at this, I want you to look at this a little bit. What are the inputs here when you train? So this is my training data. This is my X-train data, okay? It's a matrix. I vectorize all my samples. Each sample is represented by a set of features. So I did one here because we have the compact form, the bias. So we have like, actually, this is, you know, the X tilde is the we can call it X also if we want to stack all of them, but we have the bias basically, which is a bunch of ones. So the bias here is like this. So the first feature is all ones. All right, okay. And then here we have our bias, we call W0, and the rest are W1 until I get WD. Okay, so I have D plus 1 weights. And then here I have N samples. These are the number of samples. So for each dog, I'm predicting the value right here. So what is happening? It's quite interesting that you have a diversity of images. Look, you have images like this, and you want to see if there is a dog or not. Different type of images, but still you apply the same model, the same weights to get a final score. Isn't that impressive? Basically, think about it, guys. We have a bunch of weights, D weights, for every single feature, in my original data, okay? Before I vectorize it in my original image, for every single pixel, I learn a weight, and that weight will allow me to transform this whole feature vector that can have thousands of values into one single vector, one single value through this matrix multiplication. All right. So what does that mean? It means somehow we have discovered a mapping. Okay. So we discovered a mapping function or transformation here, which is encoded in this weight vector W that is D-dimensional, that allows me to map every single input xi into yi. But if it's good enough, it will allow me to predict all ranges of ages, right, that I have in my data. And this is a universal fixed mapping for my training data. This will not change. This guy will map everyone inside my matrix and will predict everyone inside of my output target vector. Okay, so it's about learning this it's about approximating a universal function that will work on all kinds of images. If we were able to see all kinds of representations of dogs, and then, you know, hopefully we'll have a good approximation that is generalizable, which means it generalizes to unseen, you know, data or images, which is basically the test set. Okay, so it's a single vector that we are after here in linear regression. So now in nonlinear regression, what do we have? If the relationship between x and y is nonlinear, so we go from simply having a linear model that approximates the relationship between the x and the y, the input and the output in this regression problem. So remember, as I mentioned, so in regression, this will represent the input data, and the y-axis is actually what we are after. So this is what we want to predict. Okay. So if we have, for example, a nonlinear relationship, which means we don't have a line, we have a nonlinear relationship. So for example, here, if I look at this, I would, I need to learn this new mapping, this new transformation, this new model, and my model now has become nonlinear. So maybe here, f of x will be equal to x squared, which is a parabola, right? Plus a bias because it's shifted, it's not centered at 0. So we have some bias there. So we have some, shift. And this would look like, for example, my model. So when I plot the data, I may try to guess which transformation I need to apply, which nonlinear transformation I need to apply to be able to fit the model. But as I mentioned, if we cannot see the data because the data lives in a highly, highly dimensional space, how can we get this f, right? It's a big question. So now we can see the data because it's x belongs to R, right? It's one feature, one single value, right? But if you have a d-dimensional x, you can't even visualize the data, right? If you have d features of the input data, this is an infinite kind of, it's like a high dimensional space. You will not be able to see the data like this, right? So it's difficult. And you may not have, if you don't have a good intuition about which transformation, that might be not a good starting point. So here, if we have some good intuition and we know that, for example, we assume we have a prior knowledge about the model. So we know, for example, it's going to be quadratic or a sine wave or logistic. So we can make this assumption and say, we're going to try to fit a quadratic model to my data or a sine wave model to my data. All right. So based on that assumption. So these basically, they belong to a family of nonlinear functions. And we want to identify or find these functions to be able to learn this model that we want to discover, f of x, a transpose w. So let's look at this together. So we can write this model in this way. So how do we write it? So this is an important notation because we will use it in deep learning later. So we have basically the input data x. So this is my input data. We'll use a different. So this is my input data, input sample. And here we have what we call the parameter theta. So theta basically contains all parameters. So let's look at this. First, we have kind of the bias, W0. And we have a set of functions, okay? So these functions, they will map, the data x into new dimensions, into new space that has b dimensions. And these have b weights. So basically, what we have, we go from a d-dimensional space, okay? So d-dimensional space to that could have, for example, could be R3 to a new space where we have b bases, okay? So it's less. So here we go to b-dimensional and like it could be R2, for example, all right? So you can write this, of course, you can write it in the matricial form in using linear algebra, and this would be a good exercise for you guys to try to write it in this form. Okay, so I won't write it for you here, but you can easily write it. And then once you do, so here what we have, basically, we have different parameters. So we do have the W parameters. These are the internal parameters. These are the, external parameters. So W0 to WB, okay, all these parameters. And we have what we call internal parameters of functions fi. So all these functions might have external, some, like additional parameters. So we stack all of those in the vector theta. So theta basically is what we are after. So we want to learn the theta. And if we learn the theta, then what happens if I have, for example, a data distribution like this? let's say I'm going to do it something maybe a bit funny. And if I learn the theta, I will be able to discover my, you know, like regression function nonlinear model that will look maybe like this. Okay, so that's what happens when we optimize and we get the optimal theta that has all optimal parameters. So now how we're going to do that, of course, loss function and then gradient descent. So what you guys notice is basically this is a linear combination. It's a weighted linear combination. So here we have, these are the coefficients of our transformations, of our nonlinear transformations. And how many nonlinear transformations? We have B nonlinear feature transformation models. So we're trying to transform the features from a space where they are, you know, like where they are represented nonlinearly into a very, you know, like smaller space, as I mentioned, B-dimensional, that allows us to do the regression better. So if we look at this, this is quite simple. So you can write it in the compact form. And here we go. If you write it in the compact form, it's actually very, very simple. This is the beauty of linear algebra and math, that now now we replace what we had before. If you guys remember the linear model, we had directly the X data, the data point itself, right? And the W. So now what we have is a transformed feature vector. So we transformed this, you know, like into a new representation, and we hope that now we can better fit the data. And this is a nonlinear model. So the nonlinear model is represented as this vector, right? So the dimension here is actually B plus 1. And we have, you know, W, B. So we have like, you know, B plus 1 also waits to learn. So what does that tell us here? So if you think about it, when we transpose this, right? So you have basically what you're going to have is a, you know, like if you do the matrix transform, we're going to have, you know, like the same number of the values that we want to predict. So the Y will not change. What is actually changing here? If we do the transformations. So if I take this example right here, what is actually changing is two things. First, we don't have the X. This will be called F, right? Okay. And then we don't have D features. We have B, right? And then the number of weights here will be B weights. So, and it's up to you guys. You can rewrite this properly and neatly. And we will see this in detail in the summary, because the summary is very neat. So, okay, so now, basically, we know how to represent this, and the goal is to learn this model. So we want to learn this model, and this model is parameterized by theta, and it takes as input the X, and you know, so this is F actually applied to X, so it's not written explicitly, but it is applied to X. So F transforms the original features, and this is the loss. We can have a simple loss function. So this is our loss function. It's the least squares. What did we change? It's just, you know, we have now the yi hat predicted, but this is predicted by a transformed, basically, original feature vector through fi. So basically, fi is fi of x. So for example, let's see an example. So if we have the original x right here, and we have 1, and we have different values, we have d values. And if I want to transform this, right, and I apply f, you know, like to my sample xi, okay, so fi, then I'm gonna get a just b plus 1 values. So these are b values, and I have 1 here, okay, so b plus 1 values. And this is, you know, the value here is fi, okay, fi of x, for example. Let's call it here, this is I element k, Okay, this is xi element k. So this transformation could be something interesting. We can have b equals to d and then apply, for example, a sine function. So if I apply a sine function, or if I apply, for example, a quadratic, right, then I'm gonna square all of these, and then that's my nonlinear transformation, right? And I preserve the number of features. But here we can also change the number of features. We can make them smaller, like b usually it's smaller. So we have different ways of doing this, and this is actually what we call dimensionality reduction. So you're basically mapping the data into a lower dimensional space through this transformation. So now this transformation is very important because it allows me to get a new representation of the data. So this is a new representation of the data, and these are basically the you know, like the values that we have, the coefficients in this new space. Okay, the weights that we want to learn. All right, so now we're gonna go further and ask this question. So how to determine the appropriate feature transformation? So I asked this before. How can we find the appropriate feature transformation for our model? So, and how can we find the number, the optimal M number, the best, you know, number B? How many feature transformations do we need, right? Do we need, you know, the same number of features, or maybe less? Maybe not all of these guys are important. So how can we fix the B for any generic data set? So this is a big problem. And like usually what we rely on is, as I said, is our intuition. So you know, the B, you can try different values, but you can tweak that. And when we get to the session where we talk about how to design neural network architectures, these are actually hyperparameters that we need to identify. How many weights we want to learn in each layer, for example, what is the appropriate transformation, what is the appropriate, for example, nonlinear transformation? Should we use a ReLU? Should we use, for example, another type of transformation? So that's important. Now let's look at this to just summarize the regression before we move into the multi-regression quickly. So here we have a linear model. This is our data. We multiply it by, you know, like the learned weight over here. And then what we have a, you know, like a simple linear function, weights to learn. As for the nonlinear model, we change the dimensions. So we have b plus 1. All right, sorry about the color. Let me choose another one. So we have b plus 1. All right, and then there is actually a mistake here. So can anyone spot it? Enhancement. So what is the mistake right here? So I'll give you
the W.
The W, yes, very good. So the W is b plus 1, thank you. So we have the W here, and it's actually b plus 1, so for consistency, and which means now we are learning b plus 1 weights. This is a smaller mapping function, right? A smaller like approximator compared to the original one. And however, the number of samples, they should be the same. So if these are the number of samples, they should be actually the same. Okay, so these are the number of samples, and here the number of new represented features should be the same. All right, so that's our nonlinear model, and now we have the transformed feature matrix. So this is the transformed new feature matrix. Okay, and this is what we call the new representation, and we have a new space where we represent this, you know, using these, basically this mapping function. All right, cool. Now, so as an answer to the solution, how to find a transformation. So you can try to guess. So which means you try to find, guess the type of nonlinearity based on the data visualization, if you can visualize, right? And here you can see, for example, a sine function will be good to approximate. You can also, you know, like try to use other Simple means, as you know, for example, prior biological assumptions or prior knowledge, domain expertise that you have about the data. So interestingly, what happens here is you guys, so this is what I want you to, now I want you to focus on this a little bit. So what we have a sign function, all right, that we fit into the data. And this is the sign function. So it has two parameters, V0 and V1. So these are the parameters that we want to estimate. So if I'm going to write my theta vector, it has basically V0 and V1. All right, very good. So now what happens that in the original space, we have a nonlinear relationship, right? We agree on that. Now, in the new space where we take the transformed feature, so in the new transformed space, right, we have a linear relationship, and you guys can see it right here. So somehow what happened that in the original space before transforming, I have this nonlinear complex transformation. I can have something like that. Imagine relationship between X and Y, right? So it would be very, very difficult to approximate. But what is wonderful about having a prior or discovering the right F, the good F, if I get the right F, I will be able to transform a nonlinear complex relationship into a linear, simple relationship, basically. And this is what deep learning does, and we'll discover that more together. So it transforms the data hierarchically into a space where a simple classifier, linear classifier, can work at the very last layer, at the very end of it. So, however, this function, how are we going to approximate it? How are we going to learn and approximate this function? It's a big question here, because if we get the right function F, the right transformation, as we have here, because here we actually know it's a sine function, right? But if we can get it very well, our problem becomes so easy to solve, cheaper to solve, and also, you know, like easier to solve.